The Refreshable PDB Switchover capability allows us to define replicas on a per-PDB basis with only 2 CDBs to manage. We might start by creating a PDB named red in CDB1, and then simply creating a replica of this in CDB2 using the familiar Refreshable PDB syntax. We might add a few more PDBs, gold in CDB2, brown in CDB1, and grey in CDB2. No replicas are required for gold and brown, but we want one for grey. And as simply as that, we have 2 pairs of replicas being refreshed in opposite directions between these 2 CDBs. Now we come to the Refreshable PDB Switchover capability. There are several ways in which this can be very useful. For example, planned switchovers can be very helpful for load balancing. These resource meters show uneven load distribution between the 2 servers. The role transition is executed as follows. Connect to the current primary. You may find it helpful to think in terms of connecting to the future replica, and issue this statement: alter pluggable database grey, refresh mode every 2 minutes from grey at dblink switchover. The syntax to set up the refreshable clone is familiar, and here I introduce the new keyword switchover. User connections will now be to the new primary, now in CDB1. In this example, we've seen how trivial it is to perform load balancing with this capability, while maintaining a replica on a remote server, just in case. In situations where the primary PDB fails for some reason, we can switch over to the replica and resume operations there. We refer to this as an unplanned switchover. The 3 steps to perform the role transition from replica to new primary are as follows. Perform 1 more refresh of the replica. Remember that, although the source PDB is no longer available, the refresh process involves reading redo from the primary CDB's redo stream, online redo log and archive redo log files. For the purposes of this discussion, we assume that the source CDB, including its redo stream, is intact, and that the failure is confined to the source PDB alone. Therefore, it is reasonable to assume that this final refresh will succeed. What it achieves is to transport and apply any transactions that were performed against the primary between the previous refresh and the PDB's failure. Alter the surviving replica so that it is no longer a refreshable PDB. Open the former replica read-write so that it can be used as the new primary. Let's consider the high availability implications of this capability. In the sense that it can be used to maintain a replica in another server, we've seen how a refreshable PDB may be used as a replica on which operations may be resumed, whether the switchover is a planned or an unplanned event. In that sense, it's worthwhile to consider the characteristics of a switchover from the point of view of recovery time objectives, RTOs, and recovery point objectives, RPOs. Recovery time objectives consider how long it takes before operations can resume in the event of a switchover. In other words, how long is the outage? The point is that RTO is affected by the amount of redo to be applied. In turn, that is a function of the rate of redo generation in the source PDB and the frequency of refresh of the replica. The worst case is a failure of the source just before the next refresh was due to have occurred. Assuming a relatively steady rate of redo generation at the source, this situation is likely to result in the maximum amount of redo to be applied to the replica before a switchover can be completed. In general, a relatively high frequency of refreshes, of the order of every couple of minutes rather than every few hours, is likely to leave relatively little redo to be applied before a switchover can be completed. It is important to test thoroughly with realistic transaction volumes to ensure that the process of refreshing the replica can keep up with the rate of redo generation. Recovery point objectives apply to how much data is lost in the event of failure of the primary. In many cases, the failure of the source PDB alone will not cause any data loss. As long as the source CDB remains operational, all committed transactions should be protected in the online redo logs and archive logs of the source. It is therefore likely that even transactions that had not been applied to the replica at the time of failure of the source PDB can be recovered and applied to the replica before switching over to that. The worst case is a total failure of the source CDB or its host server. In this case, the online redo logs, and potentially even the archive logs on that server, are inaccessible. With the basic Refreshable PDB capability that I've described so far, there is in this and similar situations the possibility that all transactions that happened on the source since the last refresh will be lost. For example, if the Refreshable PDB had been created with this statement, create pluggable database myPDB from myPDB at dblink, refresh mode every 2 minutes, the maximum data loss is 2 minutes of transactions. This assumes that the refreshes had been able to keep up with the rate of generation of redo from the source. However, another strategy exists through integration with a DataGuard remote redo repository, a component of DataGuard FastSync. This possibility arises because the Refreshable PDB can read data either over a database link from online and archive redo logs on the primary, this is what we've seen so far, or from a remote redo repository maintained via DataGuard's redo transport. This slide illustrates how this works. Here, DataGuard is the only component involved in scanning redo logs on the primary and transporting them to a remote redo repository. Having defined the Refreshable PDB as before, we now modify it to be refreshed from the remote redo repository. This second option has several important advantages. It minimizes the impact of scanning redo logs on the primary. It minimizes the amount of redo transport between CDBs. It enables near zero data loss in a failover situation. It may seem paradoxical, but high availability and disaster recovery are not necessarily the same thing. Let me explain. As discussed earlier in this video series, online PDB relocation allows a PDB to be moved between servers without taking an outage in the PDB. However, we've also seen that moving a PDB into a CDB protected by DataGuard can be complicated because we also need to consider setting up the corresponding replica in the standby CDB. We could relocate the PDB into the DataGuard primary with standbys equals none, but then by definition there would be no standby PDB. So in this case we'd have a high availability or HA relocation, but a vulnerability from a disaster recovery or DR perspective. On the other hand, the transient no standbys PDB technique can be used to set up that replica, thereby ensuring that we have DR. However, since this technique involves cold cloning, it is not a high availability operation. Therefore, in this case we have DR but not HA. We want our cake and eat it. To resolve this dilemma, we can use Refreshable PDBs. Let's say we want to migrate PDB red from top to bottom, as shown here. We start by creating a Refreshable PDB in the CDB to which we wish to relocate. Of course, this serves as a replica for DR purposes. If the top CDB fails, we can recover using the replica in the bottom CDB. When we're ready to relocate, we execute a switchover. The associated role transition achieves the desired result. The red PDB is now in the bottom CDB as a primary. Its replica in the top CDB can be used for failover purposes in the event of a disaster.